it is clear by now that Monte Carlo simulation requires an abundant supply of IID random numbers. We did discuss this, the various methods of generating random numbers earlier in this course in part A, and it was quite clear that true random number generators, those that use physical sources, are not really appropriate for our purpose in science and engineering and structural reliability that we are looking at now. And we need pseudo-random number generators, generators that run on a computer. They produce a sequence of IID uniform deviates, standard uniform deviates, as the output of a very precise and deterministic computer algorithm. But very importantly, this sequence has all the appearance of a true random number sequence. So properties of a good random number generator are quite a few, and the ones that we are particularly interested in would be, of course, accuracy, the ones that are highlighted in bold, a long period, which we have discussed what it means, machine independence, and repeatability. Basically, a code that you write and get some results, if I use that on my computer, I should be getting the same exact results, and thereby we can verify each other's results. We have been talking about Matlab in this course, and RAND, as we have seen already, is the command in Matlab for generating standard uniform deviates. The default generator is the Marsan-Twister algorithm. The default seed is 0. If you want to change the seed to any other particular value, if you want to start with a random seed, so to say, you can use RNG command. RNGN sets the seed to the number n that you want, and if you want to take the seed from the system clock, then you use RNG shuffle, as you see on the screen. So with these standard uniform deviates, we need to now set up and undertake Monte Carlo simulations for all kinds of problems. So obviously we cannot stay confined to uniform deviates. We have to convert them to distributions of our choice, or the ones that we need. So there are various methods of generating random deviates from non-uniform distributions, and the inversion method is the most popular, and it's the simplest to use, and it's very general. All it says is that if you are able to generate standard uniforms, and then if you can invert any arbitrary distribution function, then that would give you the deviates from that arbitrary distribution. So here are the steps pictorially. On the left, you see the uniform density function, the standard uniform density function that takes on values between 0 and 1, and then that basically corresponds to the CDF, the arbitrary CDF fx, which also takes values between 0 and 1, and then suppose u1 is the first uniform deviate that the computer gave us, and then we take that, come to the red line, which is the CDF of x, invert that at that value, and we get x1. So that's how we invert u1 to x1. The next one could be u2, and that gives us x2. Likewise, u3 gives us x3, and so on. This method can be very useful, but there are certain drawbacks. You need to be able to invert the CDF f quickly and accurately. If the inverse is not available in closed form, so obviously there could be convergence issues. In such cases, and the normal distribution is obviously the most celebrated example of that, we have to use other methods for accuracy and speed. When you have discrete random variables, we can use the same inversion method, but we just need to remember that it's not a smooth function. The CDF is not a smooth function, it's a step function, and when we invert we have to keep that in mind. So for example, you see a series of these steps, the CDF of x, the discrete random variable x, and if we generate say u1 as before, then we read off the CDF curve and see which step it belongs to. So all these steps are basically left continuous, so we make sure to get that particular value. You can see u1 gives us x1, u2 gives us x2, and so on, as we had in the continuous case, but here the comparisons have to be done carefully. Here is the algorithm detailed out. So you see, you keep comparing until the first time the cumulative PMF, the CDF, exceeds the random number generated, the standard uniform deviate generated for the very first time. So that gives us the value of x to be returned. Let's look at a few examples of this inversion method, how we can code that. So let's take two examples from continuous type distributions. Let's say we want to generate an exponential with parameter lambda, our starting point being a standard uniform deviate. So we will generate the uniform u and then equate that to the CDF of the exponential. So that gives us 1 minus exponential minus lambda x is equal to u. And that we can invert and write x as negative 1 over lambda times log of 1 minus u. In some texts, and this is also a very good practice, you will find that instead of log of 1 minus u, you will find log of u. And the reason is that 1 minus u it has the same distribution as a standard uniform deviate, obviously not identical to u, but for our purpose it serves the same way, and the benefit is that for every time we generate x, we don't have to do that subtraction operation. We can just start with u, so that shaves off some time from the computational load. Next example we can look at would be to generate a Gumbel. By the way, this is the Matlab code that we can use to generate such exponentials. We have seen this actually earlier in part A. So suppose we want to generate 100 of these exponential deviates, and this would be the command. You see the rand command, which is the Matlab call to the uniform generator. Let's next look at how to generate Gumbel deviates. Let's say we have x, a Gumbel random variable defined by the two parameters alpha and m, and we need to sample deviates from that distribution. So same process, using inversion, we generate the uniform u, standard uniform, and then invert the CDF of the Gumbel at u. So going through the algebra, x would be m minus 1 over alpha times log of minus log of u. And this is the value that we would return. The code would look something similar as you see on the left. We would have a call to again rand and keep doing it until we have generated the desired number of samples. We could use the inversion method also to generate normals, but that would not be very desirable because the normal CDF cannot be inverted in closed form, although you can call such functions, but it is generally a little expensive and sometimes there could be convergence issues. So there are more efficient ways of generating normal deviates. One is the box Muller transform. We did discuss this earlier in this course. The other is the acceptance rejection algorithm, which uses the Laplace distribution, etc. The Matlab command is rand n, and it also uses the Marson-Twister algorithm. Now, this rand n gives us, or all the other methods that you see, they give us the IID standard normals. So if we call them z, then we need to transform these z's to any arbitrary normal, and there we would use the property that the normal distribution is closed under a linear transformation. So if we want to generate a normal with mean mu and standard deviation sigma, then we would just multiply that z with sigma and add mu and obtain the desired normal deviate. We could generate correlated normals starting from independent standard normals, and let us say we want to generate a vector of n jointly distributed normal variables whose mean vector is mu and the covariance matrix is Vx. So we are going to again use the same linear transformation that we saw, but in reverse order. If we have any random vector x and we do a linear transformation on that, we would get a new random vector y with mean and covariance that you see on the screen. Now, if the x's are jointly normal, then y is joint normal as well, that we know. And now we use the special case that the size of y and x are same, so m equals n. The mean vector of x is 0, and the covariance matrix of x is the identity matrix. So what we are getting at is that the x's are basically the independent standard normal vector. So if that is so, then y has a mean which is a0, and y has a covariance matrix which is a transpose, and a was the matrix that we used to create y. So this tells us that we can actually take this approach to generate any correlated normal vector. All we have to do is we start with the IID standard normals and then choose a to be the lower Cholesky factor of Vy, which is what we desire, and then multiply a with the z vector and add to that a0, that is the mean vector that we want, and we have the desired n-dimensional correlated normal. Let's move on to Monte Carlo simulations using the inversion method for discrete random variables. So the general algorithm is this, that we generate the standard uniform u, and then let's say x is integer valued, So we set x equals 0, and then f is, let us set f at p0, the very first PMF. And then as long as the CDF has not exceeded u, we keep going through the loop, and the very first time that CDF exceeds the uniform deviate generated, we exit the loop and return the value of x, the integer. The mean number of comparisons is mean of x plus 1, so it could get a bit computationally intensive, but that is the price of using the inversion method. We could generate a Bernoulli random variable very simply in one step. We generate the uniform u, and if p is greater than u, we return x is 1, or we return x is 0. The next set that you see is the binomial. We do a similar comparison until we succeed, but here we have taken a slight change in the algorithm which speeds up the process a little more. That CDF that you see, px being replaced by its current value times p over q times n minus x plus 1 over x, so that speeds up the computation of the CDF. We could set up a similar algorithm for the Poisson deviate as well. So all of these use the inversion method.